The topic of the talk is common crystal structures. Among crystal structures of each element of the table of elements, some structures are especially common. When we see the periodic table of elements, we find that the crystals in that table will have few common structures or few structures which are very common. Among them are face-centered cubic, which we call as FCC in short. The other one is body-centered cubic, BCC in short. And the third one is hexagonal close-packed SCP. Since the explanation of these three will be simplified, if we once revise the simple cubic, hence four structures are listed here. This is the simple cubic. We believe that every atom is like a sphere, and when there are two spheres like this, on one side their circumference will touch each other. Similar way, this is shown with more clarity that atoms are at the edges of a cube. But practically if we see, the cube has 8 atoms at their corner, but the presence of each atom within the cube is only 1/8. Similar way, we have face-centered cubic FCC, where every face of the cube has got an atom at the center. In this figure, the corner atoms are shown in green and the atoms which are on the 6 faces are shown in red. Here the view says that the atoms that are there at the corner are 8, but presence of each atom within the cube is only 1/8, and the face-centered atoms are half within the cube, and the remaining half is cut because of the wall of the cube. Similar way, we have body-centered cubic, where one atom is there at the center of the body of the cube and 8 atoms could be seen at 8 corners of the cube. Practically, each atom's presence within the cube at the corner will be only 8th, whereas the center atom will be a complete one. And one more which we have is hexagonal close-packed crystal, which will have 3 planes. At the bottom there is a hexagon, and every edge of the hexagon has one atom. At the center, one atom is there. And in the upper plane, there are 7 atoms similarly. And there is a middle plane where 3 atoms are there. Practically, you could see this way, only those which are there in the middle have their complete spheres, whereas the upper atoms and the bottom atoms are partially present in the SCP. Now we focus each and every structure that we have just now summarized. Simple cubic, as it is discussed in previous talks, that it will be a cubic with sides A, B and C and interaxial angles alpha, beta and gamma. A, B and C are equal and alpha, beta, gamma are equal and of 90 degrees. This is the simplest unit cell and is called as simple cubic. This crystal structure is just a cube with an atom on each corner. There are 8 atoms at 8 corners, but within the cube, each atom presence is only 1/8. As said, there are 8 atoms at 8 corners of the cube, but practically the cube will be having only 1/8 part of the atom in the body of the cube. Hence in total there are 8 into 1/8, that is equals to 1 atom per unit cell. The simple cubic unit cell is also called as primitive cubic and thus abbreviated as CP because it is the most simple one, the most primitive one. It is also called as primitive cubic and in short it is mentioned as CP. The unit cell is the simplest for people to understand, however it rarely occurs in nature due to its low packing density. The simple cubic is very easy to understand for those who are interested in learning crystallography, hence the explanation starts with this. This is taken as the basic or simplest cubic cell. However, practically speaking, the atoms presence in the unit cell will be lesser, their volume will be lesser, hence the total density of the atoms within the cube is lesser. Hence in nature such simple cubic crystals will be existing very rare. There is a term called as number of nearest neighbors in a crystal. In case of simple cubic it is 6. Here if you see the diagram, there are several simple cubic crystals connected to each other. If we focus on one, that is purple one, we find that this is nearest, this is nearest, this is nearest and this is nearest, and above one this is nearest and below one it is nearest. Because the simple cubic has 6 faces, it will have 6 nearest neighboring atoms. So also every other crystal will have the term defined with it called as nearest neighbors. This is the animated simple cubic crystal where it is explained how the partially cut atoms within a cube get connected to the partially cut atoms of the neighboring cube and so on. This way the total crystal lattice will form. Few more details are discussed here. We use the hard sphere model in the sense each atom is considered as hard sphere, which imagines each atom as a sphere. The simple cubic crystal has each atom touch along the edge of the cube. Since each side of the unit cell extends from half of one atom to half of the other, the side of the cube or lattice constant represented by A is just 2r, where r is the atomic radius. If you focus on this picture, this is the radius of the atom called as R, and here this is the side of the cubic cell, which is A. This is also called as lattice constant or lattice parameter. Now I describe a parameter called as atomic packing factor, in short APF. This indicates the density of atoms within a crystal. APF is defined as volume occupied by atoms by volume of the cube, in the sense how much volume is occupied by atoms in the cube divided by volume of the total cube. In other words, APF is equals to number of atoms within the cube into the volume by volume of total unit cell. The volume of a sphere is equals to 4 by pi r cube. Since there are 8 into 1 by 8 atoms in a cube, hence volume occupied by atoms in a cube will be 1 by 8 into 8 by 4 by 3 pi r cube. That is simplified to 4 by 3 pi r cube. Volume of the unit cell is A cube, and we know that A is equals to 2r, hence it becomes 2r to the power of 3, that is equals to 8r cube. Hence APF of simple cubic is 4 by 3 pi r cube divided by 8r cube. This comes to pi by 6, and that becomes equals to 52%. It implies in the total unit cell, the volume occupied by atoms is hardly 52%. It is hardly 50% of the unit cell that is occupied by atoms, and the remaining percent is vacant. The second crystal structure under focus here is face-centered cubic, called as FCC in short. In face-centered cubic, there will be 8 atoms at the corner, and as the cube has 6 faces, at the center of each face, 1 atom will be there. If you focus on right side figure, the corner atoms are showing only 1/8 presence in the cube, whereas the face-centered atoms are showing their presence 50% within the cube. Face-centered cubic is also called cubic close packed, in short CCP, as it is the closest packed cubic arrangement of atoms. FCC is a cube with an atom on each corner and another on each face. Hence there are 4 atoms per unit cell. Here is an animation of face-centered cubic, that one cube, when get connected to its neighboring cube, the face-centered half atoms will be completed. Similar way, the atoms that are at edges will also get completed with the help of neighboring unit cells. Now we compute APF for face-centered cubic. As described earlier, APF is volume occupied by atoms by volume of the cube, that is nothing but number of atoms into volume occupied by them by the total volume of unit cell. As discussed, the volume of a sphere, that is the volume of one atom, is 4 by 3 pi r cube. Since there are 8 into 1 by 8 corner atoms plus 6 into 1 by 2 face-centered atoms, hence the total number of atoms in the cube are 4. Hence volume occupied by atoms in a cube will be 4 into 4 by 3 pi r cube, that comes to 16 3 pi r cube. Now volume of the unit cell, as we discussed, will be A cube, and A is computed in terms of R, and that comes to 2 root 2 into R whole cube. Now if you see this figure, we have a face-centered cubic lattice above. This is the diagonal, which is indicating that there are 4 R's here, in the sense this atom has 1 R as radius. The central, that is the face atom, has got 2 R as diameter, and this is 1 R. So altogether the length of this diagonal is 4 R, and this side, as we have already discussed, is A. Hence we draw a triangle where the diagonal is 4 R and 2 sides are A, because this cubic has other sides as also A. Hence using the Pythagoras theorem, 4 R whole square is equals to A square plus A square, that comes to 2A square. Hence A is equals to 2 root 2 R. This value of A is substituted here to get the volume of unit cell. Now APF of FCC is nothing but the volume occupied by the atoms in a cube, that is 16 by 3 pi r cube, here it is written, divided by the volume of unit cell, that is nothing but 2 root 2 r whole cube, that comes to pi divided by 3 root 2, and this comes to 74%. Implies that in the unit cell the atoms are occupying 74% of the space and remaining is left vacant. Now we focus on body-centered cubic. In the body-centered cubic, we find the edges of the cube has 1 atom each, and at the center, that is at the body of the cubic cell, we have 1 complete atom. If you see the practical view, the corner atoms are only 1/8, so they are forming 1/8 into 8 atoms, and the middle atom is complete in itself. Body-centered cubic is the third kind of cubic structure. This is nearly close packed. BCC can be imagined as a cube with an atom on each corner and another atom in the center. Hence there are 2 atoms per unit cell in BCC, as discussed in previous slide. This is the animation of body-centered cubic, that one unit cell with the cut atoms at the corners are getting completed when the neighboring unit cells are connected to them on different sides. Here the calculations of atomic packing factor are shown with the help of these diagrams. Here the body-centered cubic is shown, whose lattice parameter is A and the radius of the atom is R, and the whole BCC is elaborated with the space in between for understanding. Here you could see one diagonal at the bottom surface in blue color and one diagonal which is crossing the body-centered atom and is touching the other side edge of the cube. Hence there are two triangles forming. One is from purple to purple atom, then to the bottom yellow color atom, then back to purple. That is shown here, and as it is discussed that this diagonal size will be 4R and the lattice parameter vertical is A, and the diagonal that is shown at the bottom is assumed as D. When we apply the Pythagoras theorem, it becomes 4R square is equals to D square plus A square. It implies A is equals to 4 by root 3 into R. The other triangle we get from the bottom of the cubic cell. The diagonal which is in blue color is shown here as D, and two sides are shown as A and A. Here also when we apply Pythagoras theorem, it becomes D square is equals to A square plus A square, that is 2A square. Now all these calculations and information we substitute to get APF. The volume of a sphere is 4 by 3 pi r cube as discussed. Since there are 8 into 1 by 8 corner atoms plus 1, that is body centered atom, the total number of atoms will be only 2 in the cube. Hence volume occupied by atoms in the cube will be twice of 4 by 3 pi r cube, that comes to 8 by 3 pi r cube. Volume of the unit cell is A cube, and just now A is calculated as 4 by 3 r whole cube. Hence APF of BCC is 8 by 3 pi r cube divided by 4 by root 3 r whole cube, and that comes to root 3 pi by 8 is equals to 68%. It implies that the density of atoms within the cubic cell is 68%. Here characteristics of three lattices are summarized, those lattices which are just now discussed. One is simple cubic, one is body-centered cubic, and one is face-centered cubic. Volume of unit cell is A cube in all. Atoms per unit cell is 1 in simple cubic, 2 in body-centered cubic, and 4 in face-centered cubic. Atomic radius R is given by A by 2 in SC, and root 3 by 4A in BCC, and root 2 by 4A in FCC. Nearest neighbor distance, that is 2R, is equals to A in SC is equals to root 3 by 2 into A, and in FCC it is A by root 2. Number of nearest neighbors is 6 in SC, 8 in BCC, and 12 in FCC. The one crystal that is left here is hexagonal close packed HCP, where there are two planes, one at the top and one at the bottom. Bottom has 7 atoms including the center one. Similar way, top has 7 atoms including the center, and the middle plane has 3 atoms. Since the syllabus on crystallography is mostly about cubical systems, only few fundamentals of this topic will be explained here. This is the animation of hexagonal close packed. It is very obvious that the top plane has 7 atoms, bottom plane has 7 atoms, and the middle plane has 3 atoms. Hexagonal close packed is the only non-cubic crystal structure discussed here. SCP is like a hexagonal prism with 3 atoms in the center. It is like a hexagonal plane stacked on top of another hexagonal plane, stacked on top of a third hexagonal plane which matches the first one. We discuss volume of hexagonal prism when we need to compute APF. However, volume of hexagonal prism computation is shown here. This is the hexagonal crystal where one side in the hexagon is A and the other side is B, and the height is C, and it is understood that A and B are equal and they are equal to 2R, and the height C is given by 4 into root 2 by 3R. Now the bottom is taken into consideration, which is a hexagon, and there are 6 triangles in that hexagon. If we could find the area of one triangle, then just by multiplying it with 6 we get the total area of the hexagon, and when this area is multiplied by the height C, we get the volume of hexagonal prism. These calculations are shown here. Focusing this hexagon, this is shown as height h, this is A, and this is A by 2. Applying the Pythagoras theorem to this small triangle, we get A by 2 whole square plus h square is equals to A square. It implies h is equals to under root A square minus A by 2 whole square. Now, We are discussing these details here. Volume of hexagonal prism is equals to area of hexagon into height of the prism. Hexagon is made up of 6 triangles. Area of each triangle is to be calculated. Area of triangle is half base into height. That comes to half into a into h. That is nothing but root 3 by 4 a square. These simplifications are taken from here. Area of hexagon is 6 into root 3 by 4 a square. That is equals to 3 into root 3 by 2 a square. Volume of the unit cell is equals to area of the hexagon into C. Area of hexagon is 3 into root 3 by 2 a square, where C is the height of the prism given by 4 into root 2 by 3 r. Hence the volume of SCP unit cell is 24 root 2 r cube.